All right, so let's carry on with some more challenging related rates questions. So here we are on page 20 of the note package. Okay, so this one has to do with volume, three-dimensional things. So the drawing is a little harder to do. If a snowball melts so that its surface area decreases at 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10. You might want to read that to yourself again. Let me read it. If a snowball melts so that its surface area decreases, so let's call that A, surface area decreases at a rate, so it's getting smaller, the area is shrinking, find the rate at which the diameter decreases. So we need a picture. At least I need a picture. Some people maybe have a more conceptual mind and they can sort of deal with it just with words, but I find it much easier to draw a picture. So let's actually, so we have the area, which is kind of um, it's hard to sketch what we mean by area. So the this is the area, surface area A on the outside. And usually we talk about radius in a circle. So let's actually draw the radius too. And then the diameter would be, well, let's draw it going this way so it's clear. It's just to distinguish it from the radius. The diameter goes all the way across the circle, across the sphere. Radius is just to the center. Okay, so what are we given? We're given that the surface area is decreasing at 1 centimeter per minute. Decreasing means negative 1 centimeter per minute. So decreasing is negative derivative. And what else are we given? Nothing really, right? And what we want is to know what is the derivative of the diameter. So let's call that diameter d. So dd dt. That's a bit confusing to say. dd, so the first d is the derivative, the second d is the diameter, dd dt. We want dd dt when d is 10 centimeters. That's a pretty big snowball. Okay, so then what? Now we need to write a relation. How are these things connected to each other? Well, I don't know about you, but I remember surface area as a formula involving r, right? So let's call it r. Surface area is 4 times the area of the circle, 4 pi r squared. And now, but we don't want r in there because the variable we're interested in is d. So what is r in terms of d? R would be half of the diameter. So now I've removed r from the equation. So let's see, that would be 4 pi d squared over 4. So that's actually a nice simple formula, pi d squared. Now what? I need to differentiate both sides with respect to time. Differentiate with respect to t. It's always with respect to time for related rates. Things are changing in time. So I get dA dt, and then what's the derivative of pi d squared? To bring down the 2, I'll put it right in the front. 2 pi d to the power of 1 times the derivative of d. And now what? What do we know? We need to evaluate things. So I'm given that d is 10, so I know that. I want to know dd, so this is what I want to know. And so these are all known then. So actually we're almost done. We know everything except for the thing we want. So now what is dA dt? It's -1 centimeters squared per minute. It's good to use the units because then you'll know at the end what the units are supposed to be. When the diameter is 10, and that's d dt. So I can solve for d dt. -1 centimeters per minute divided by 2 pi times 10 centimeters. What do I get? 1 divided by, be careful with the brackets here, 2 pi times 10. It's negative 0.0159 something centimeters per minute. So how are we going to state this? We could say two things. We could say it in two ways. The rate of change of the diameter rate of change is just a longer word for derivative that's a bit closer to regular language. The rate of change of the diameter is negative 0.0159 centimeters per minute. That's fine. Or we could write the diameter is decreasing at. Now when we say decreasing, that's implying a negative sign. So now I won't write the negative sign. So it's decreasing at this amount. If I said my salary is decreasing at negative $5,000 per year, that means it's increasing, right? So here I don't say negative, I say it's decreasing at this positive number. So both of these are correct. Okay, now another geometrical one. I have 1, 2, 3 more to go. All right, we'll do all 3. Okay, so we need to read the question carefully. A spotlight on the ground, a bright light on the ground, shines on a wall 12 meters away. A man who's 2 meters tall walks from the spotlight toward the building. How fast is the length of his shadow on the building decreasing? Okay, it's confusing, right? Let's start by drawing a picture. Sometimes it helps to draw the picture before you even really know what's going on. A spotlight on the ground shines on a wall. Okay, let's draw that. So here's my wall. And you don't have to be too artistic about it, but let's make it maybe a brick wall, right? There we go, brick wall. So random, there we go. There's my wall, and I have a spotlight, so some other kind of bright, maybe that's a bit big, some kind of source of light right on the ground shining this way. I don't know, how do you draw a spotlight? So maybe I'll draw a light bulb, there we go, light bulb. Shining, okay. It's on the ground. A spotlight on the ground shines on a wall 12 meters away. So maybe let's call this distance x. Well, that doesn't change, so let's just call that 12. There we go. If a man 2 meters tall walks from the spotlight toward the building, okay, so here he is. I don't know why it's a man, it could be a woman too, right? He's walking towards the building at a speed of 1.6 centimeters per second. So what we actually have to do here is we have to define this distance as a variable. He's moving towards the wall, so why don't we make this x here? The x is increasing. Okay, man walks so his height is 2 meters toward the building. How fast is the length of his shadow? Now, why is there a shadow? Well, the light that is blocked by the man will make a shadow, right? So let's kind of draw his shadow on the wall, let's say. And as he gets closer, maybe it makes sense that the shadow is going to shrink, right? When he actually gets to the wall, the shadow will be the same height as him. So let's call that maybe y, because that's a vertical length. Okay, so there's our picture. And it seems to be adequate. One thing we're going to need to do, we're going to need to know, we'll get there in a second. So what are we given? We're given that dx dt, that's the speed that the man is walking towards the building at 1.6 meters per second. And we're given the 12 and the 2, but those are already in the picture. So I didn't label those. Those weren't variables. What we want is how fast is the length of his shadow decreasing. We want dy dt when he is 4 meters from the building. So that would be when x is 12 minus 4, because this would be when this is 4 meters here, then x will be 12 minus 4. So that's 8. And that's it. So now we can write the relation here. So how do we relate x and y? Well, there's probably more than one way to do this, but one nice way is to use similar triangles. So what I'm saying here is if you have two triangles that are nested like this, well, the smaller triangle here is similar, meaning it has the same shape as the larger rectangle here. These would be similar triangles. And the ratio of the sides will be the same for all the 3 pairs of sides. That's easier to see in a formula, I think. So the side length of, let's say y, the big vertical height here, y, to the man's height is going to be the same thing as what? So vertical to vertical is going to be the same as the horizontal length 12 to the smaller length x. Y to 12 is the same as 2 to x, right? Okay, so now why don't I just clean that up a little bit? So y is 24 divided by x. Okay, now I can differentiate. Derivative of y is dy dt. What's the derivative of the right-hand side? D by dt of 24 over x. Now you might think, okay, I need the product, I need the quotient rule. We can actually do this a little bit more easily if I change that. Instead of dividing by x, I can do x to the power of -1. So then I don't need the quotient rule. I can just do the power rule. So what do I get? I get -1 times 24x to the -2 times dx dt, which is the same thing as -1 over, oh no, -24 over x squared dx dt. And now I can evaluate it. I know everything. I know everything I need to know. So dy dt when x is 4 and dx dt is 1.6 if I remember correctly, 1.6 meters per second. What do I get? I'm concerned about the units here. Let's see, the units, I'm not sure if they're making sense. Let's see. Oh, yeah, they are, because you know why? This 24 is that this was actually let's add this in. That's 12 meters. This is 2 meters. So this is actually 24 meters squared times x to the minus 1. So if I push that through to the end here, that's going to be minus 24 meters squared over 4 meters squared. This is a danger of using the units partly, but not consistently, because then you can convince yourself that you've made a mistake. So now the units are going to work out. 4 squared is 16. 2.4, negative 2.4. And I can see the units are going to be, these cancel this, meters per second. So we could say answer. The length of the shadow, that was the question. The length of the shadow is decreasing at 2.4 meters per second. All right. So most related rates problems that we're going to do are related to geometry, some kind of shape, objects moving through space, but not all of them. So we're going to do one more that is about space, geometry, and then the last one will be a chemistry example about gases. Okay, so this is a volume one. Volume. A trough, okay, in case you don't know what that means, so like a drinking container for animals. A trough is 10 meters long, and its ends have the shape of isosceles triangles. Okay, let me start drawing a picture already, because I know I need to have a trough 10 feet long, and its ends have the shape of isosceles triangles. So let's maybe draw it like this. So it's good to try to draw it three-dimensionally if you can. It can be challenging. So there's my trough. And I'm pretty good at that because I've done it lots of times. 10 feet long, and its ends are isosceles triangles, 10 feet, that are 3 feet across at the top, and so that's 3 feet across at the top. And it has a depth of 1 foot. So that would be going this way. It's 1 foot. Okay, pretty wide. So pretty wide and shallow. I'm not sure if that's realistic, but that's what we have. If the trough is being filled with water at a rate of 12 feet cubed, 12 cubic feet per minute, how fast is the water level rising? So let's imagine now that there's actually water in this trough, filling it up to a certain height. So there's water filling this thing up. And the height of the water is, let's call it H for height. If the trough is being filled with water, so we also have the volume. Let's call it V. That's the amount of water in there. If the trough is being filled with water at 12 cubic feet per minute, how fast is the water level rising? Okay, so what we're given here is that the volume is increasing at 12 cubic feet per minute. And we're given all these other dimensions, but I don't need to mention those because they're not variables. What I want is dH dt. How fast is the water level rising? I want to know that when h is 6 inches, which if you know feet and inches, that would be half of a foot. We should use the same units throughout here. So just a little side thought here. how is the height changing here? So just a little side thought. How is the height changing? Well, initially when we start pouring the water, the height will be increasing pretty quickly because the trough is not very large, because it's narrower at the bottom. So it'll fill up pretty fast. But then as it gets wider, that same volume will get spread out. So it's going to increase more slowly in height. So we're going to say that, just an observation, that H increases more slowly as time goes on. It's increasing fastest at the very beginning. Okay, so now what I need is a relation between H and V. Now, this is the first one where it's actually kind of challenging here. So what I need to know is I need a formula for the volume of water as a function of height. How does the volume depend on height? Well, what is the volume of this shape is called a prism, right? Not prison, but prism. So the volume of it's the volume of a triangular prism. Triangular prism. So it has it's going to be the area at the base, which is as a function of h, times the length in this case. So for a prism, it's the area of the face times how, well, let me do it this way. It's the area of the face on the side times the length. That'll be the volume. So this length we know is 10, but what is that, the area of the base? So for this, I think it helps to actually draw another picture. So let's draw another picture of the side view. Oops. The side view will look something like this. And now the water level, now the water is up to that height. And this is the height here. And what else do I know? I know that it's 3 across the top and it's 1 foot this way. So what is the area of this blue triangle? Well, it's always going to be, for a triangle, the formula would be base times height divided by, I can't use h, no, I can use h, so it's the base times the height divided by 2. So what is the base here? That would be this. The base is that distance there. So let's see here. We can use similar triangles again here. So similar triangles using the small isosceles triangle and the big isosceles triangle. So let me call that base B. Actually, instead of the words, I'm going to just write base times height. So this is the base, and that's the height. So the similar triangles tell us that the small base to the big base, the small base to the big base is the same as the small height to the big height. So that means that the base is 3 times the height. The base is 3 times the height in general. Okay, so I can go back up here. Base is 3 times the height. And now I have my formula for the area. So that is going to be 3/2 times h squared times 10. So let me combine those. That'd be 30, 15, h squared. That's the volume as a function of the height. All right, so you see there's a bit more work there. We have to really investigate what is the relation between these variables. Okay, now we differentiate. Left side, dv dt. Right side, 30h times dh dt. Fortunately, the derivatives are pretty easy on this one. Now what? Evaluate. I know the volume change is, what was it? The volume is 12 cubic feet per minute. And what do I want to know? I want to know dh dt when h equals 6, when h equals 0.5. When h equals 0.5 feet, and I want to know dh dt. So dh dt is 12 feet per minute divided by, what's 30 times a half? Would be 15 feet, which is, I can probably do this one myself. That would be 4/5, which is 0.8. 0.8 feet feet per minute. Now, why is it coming out feet squared? Because this 10 actually has feet on it. So this would have, I have feet here. And so let's see, this 30 is feet, 30 feet. This is feet. So that's feet squared down there. There we go. So that's feet, exactly. Got it right. So, final answer. The height is increasing at 0.8 feet per minute. Good. I like to put a box around the final answers usually. Sometimes I forget, but if you guys do that, I would appreciate it, putting a box around the final answer. Okay, how are we doing for time? Getting a bit long, but we have just one more example, and we're going to press on with that. Okay. And for these related rates questions, you really have to just practice it a lot. There's probably 5 or 10 different kinds of problems, and once you've done them, you're going to be prepared for seeing those again. And again, there's this sort of there's a limited number of different examples. So the more you do, the more likely you are to see a familiar one when it comes to the test. Okay, last one. This one, if you've done some chemistry, you'll be comfortable. If you haven't, there's some unfamiliar words. When air expands adiabatically or adiabatically, which means without gaining or losing heat. So we have some air and we're going to let it expand, but we don't let any heat escape or enter. Now, what do you think happens when you let gas expand? The pressure will drop, the temperature also drops, it gets cooler. But the main thing for this question is that its pressure P and its volume V are related. This is called an adiabatic curve, adiabatic expansion curve. So we have the relation here. The pressure times the volume to the power of 1.4 is a constant. Suppose that at a certain instant the volume is 4,000 cubic centimeters, so 4 liters, and the pressure is 80 kilopascals. And the pressure is dropping at 10 kilopascals per minute. So it's expanding, the pressure is dropping. At what rate is the volume increasing at that instant? Okay, so I need to draw a picture, even though it's hard to draw the picture, but the pressure, maybe we can draw those these arrows here. The pressure is pushing against the inside of the container. That's the pressure. And the volume is how much gas there is, right? Or how much space it's taking out. So what it's saying is that as the volume increases, the pressure is going to drop. Now we're actually given that. Now we're given the relation here, but I wouldn't put that there. But we're actually going to we're given the relation itself. So let's put that down here. We're given that P times V to the power of 1.4 is a constant. It's a different kind of given than what we're usually given. So what we're usually given is a derivative, as a time derivative. And suppose that at a certain instant the volume is 4,000 and the pressure is 80 and is decreasing at 10. So we're given that the pressure, dP dt, is decreasing at 10 kilopascals per minute. And you might say, well, we're given these two, but those are changing. So what I'll put those down here. What we want is the volume derivative at the moment when the volume is 4,000 and when pressure is 80 kilopascals. Okay, so we've organized the information. This was a little bit more challenging, took a bit more finesse. What do we do? Same as always, we differentiate both sides. So the time derivative on the left side is, we'll do that in the next step. Time derivative on the right-hand side. Let's do the right side first. Derivative of a constant, it's constant, so derivative is 0. On the left side, I need to use the power rule. So take that back, I need to use the product rule. Derivative of the first thing times the second plus the first times the derivative of the second. Let's do that in the next step. The derivative of the second. And what do I get? dP dt times v to the 1.4. How do I do the volume derivative of v to the 1.4? It's a power rule, right? So I bring down the 1.4, v to the, I subtract 1, chain rule, dv dt. Good. Now I think I know everything I need to know. Let's see, do I know dP dt? Yes. Do I know v? Yes. Do I know p? Yes. b. And this is the unknown, right? So I can solve for that. And we're just about done. dV dt is, actually an easier thing to do is just leave it as it is and then just put the numbers in. dP dt is minus 10. Kilopascals per minute. V is 4,000 cubic centimeters to the power of 1.4. Pressure is 80 times 1.4. Put that in brackets so I don't get confused. Times 4,000 to the now I regret not solving for dV dt, but it's okay, it'll work out. Times dV dt. The reason I regret it is because these units are going to get weird for a second here, but that's okay. So let me do it right now. So dV dt is going to be, I'm going to move this to the other side, so that becomes plus 10 kilopascals per minute times 4,000 centimeters cubed to the power of 1.4. And then I'm going to divide by this coefficient. All of this is multiplying in front. So that's going to go down here. So that's 80 kilopascals times 1.4, 4,000 to the power of 0.4. Okay, do you see why I did that? Because now these weird exponents are going to get a bit nicer. So what cancels? That cancels. And I have 10 over 80, so let's just call that 1/8. 1/8. And then down here I have the 1.4. And now if I do the exponent laws properly, this is the 1.4 minus 0.4 is just to the power of 1. Much better. And I forgot the minutes. There's also a divided by minutes here. Let me tidy this up here. That per minute I can put down here times 1.4. Okay, so what I'm going to get is a number, centimeters cubed per minute, which is exactly what it should be. 4,000 divided by 8 times 1.4. 357.1. 357.1. And it goes on and on and on. So there are no definite rules for rounding in this context, but these numbers all have one significant figure. So if you know significant figures, so let's round it off to, let's say 2 significant figures, just to be on the safe side. So that would be 360 centimeters cubed per minute. So we could say the volume is increasing at 360 centimeters cubed per minute. Okay, so that's the end of related rates. We just have a bunch more examples for you to do in homework. There's a few more challenging level ones towards the end of the homework, and I'll be asking you to do one of those. I'll tell you which one to hand in for next week. All right, thanks everyone.